All right, welcome to this explainer. Today we're unpacking a truly legendary piece of research. I mean, if you've ever just stared in awe at a mid-journey masterpiece or listened to a perfectly synthesized AI voice, well, you really have this 2014 paper to thank. It's by Ian Goodfellow and his team at the University of Montreal. It's called Generative Adversarial Nets, and it literally changed the entire trajectory of artificial intelligence. I am so excited to walk you through this today, because the sheer elegance of their solution to what was a massive mathematical roadblock, it's just absolutely beautiful. So let's just dive right in and break down exactly how this breakthrough happened. To really appreciate what this paper did, we kind of have to put ourselves in the shoes of early 2010s researchers. The big question, the white whale really, was simply this: how do you teach a machine to create reality? And we aren't talking about, just copying and pasting existing data. We're talking about teaching a computer to generate completely new, entirely realistic data from scratch. Stuff that has literally never existed before, but looks like it totally could have. So look at the stark contrast in where AI was succeeding versus where it was completely stalling out at the time. Deep learning was having these massive, striking successes with discriminative models, right? These are the models that categorize data. You give it a picture, it maps it to a label and tells you, hey, this is a dog or this is a cat. And they were getting really, really good at that. But generative models, the ones that were supposed to actually draw a new cat from scratch by representing these super complex probability distributions, they were struggling immensely. Why? Well, honestly, because the math was a total nightmare. They required these highly complex, intractable computations. To put it simply, AI was basically an expert at spotting a fake, but it was absolutely terrible at making one. Enter Generative Adversarial Nets, or GANs. Goodfellow and his team proposed this radically new framework that basically just sidestepped all those mathematical difficulties entirely. Like, instead of trying to directly calculate those brutal, intractable probabilities, they introduced a totally new concept, an adversarial process. They decided, hey, let's take two separate neural networks and just pit them against each other in a high-stakes game. They'd train simultaneously, learning from their own interactions rather than relying on clunky traditional math. It was a real game changer. And the authors used just the most perfect metaphor in the paper to explain this. They wrote that the generative model can be thought of as analogous to a team of counterfeiters trying to produce fake currency and use it without detection, while the discriminative model is analogous to the police trying to detect the counterfeit currency. And this competition, this is the secret sauce. The counterfeiters try to make better fakes, the police become sharper at spotting them, until eventually the fakes are completely indistinguishable from reality. So translating that metaphor into actual system architecture, what we get is a minimax two-player game. On one side, you've got the generator. Its whole mission in life is just minimizing its chances of getting caught. It wants to minimize the discriminator's ability to tell its fake data from the real stuff. On the other side, you have the discriminator. Its job is to maximize its detection rate, to accurately assign the right label to both the real training examples and the fake stuff coming from the generator. So they're locked in this relentless push and pull, constantly optimizing against each other in real time. Now, the true elegance here is the sheer simplicity of the training loop. Just look at how it breaks down into these fundamental steps. First, you sample random noise. This is literally the raw, meaningless static the generator starts with. Second, you update the discriminator, the police, by showing it both real data and the fakes, training it to spot the difference using standard methods. Third, you update the generator, so its next batch of fakes has a slightly better chance of fooling those newly trained police. And then just rinse and repeat. There's no incredibly complex math here, no Markov chains, it's just standard backpropagation. The paper actually provides this fantastic visual proof of the process in action, and it's super helpful to wrap your head around. Imagine this setup as the starting line. The black dotted line, that represents the real data, the actual truth. The green solid line is the fake data being created by our generator, and the blue dashed line is our discriminator, the police. Now, right at the start, the green line is pretty far away from the black line. The fakes are frankly terrible. And because of that, the blue line has a super easy job. It's highly confident in separating the real stuff from the fake stuff. But as that training loop repeats, the discriminator really steps up its game. You'll see that blue dashed line smooth out into this highly accurate, sharp classifier. It clearly walls off the regions where the real data, those black dots, lives, from where the fake data, the green line, currently sits. So at this point, the police are highly trained and they're operating at maximum efficiency. Okay, now watch how the counterfeiter reacts. This is the cool part. Because the police force is giving such incredibly precise feedback, it acts as a guide. The generator updates, and you can literally see the green solid line flowing directly toward the regions classified as real.
The fakes are getting better. They're starting to bleed right into the actual data distribution, slowly but surely tricking the system.
And here we have the ultimate endgame. Look at the green line now. It is perfectly aligned with the black dotted line. The counterfeiter has achieved absolute perfection. And what happens to our highly trained police? Well, the blue dashed line is now completely flat across the board. The discriminator is so baffled it literally can't tell the difference anymore. It's been reduced to guessing at a flat 50-50 rate, basically just flipping a coin. This right here is the exact moment the machine has won the game. To anchor this back to the paper's theoretical foundation for a second, the authors actually formalize this in Theorem 1. It simply states that the global minimum, the absolute holy grail of this training process, is reached if and only if the generated distribution perfectly matches the data distribution. In plain English, the probability distribution of the generated data is exactly equal to the probability distribution of the real data. The machine hasn't just memorized reality, it has mathematically modeled its underlying structure perfectly. Of course, theory is great and all, but we want to see if it actually works, right? Well, what you're seeing now are the actual outputs generated by the models trained in that 2014 paper. On one side, you have the MNS dataset, handwritten digits. On the other, the Toronto Face database. And remember, these images are entirely fake. They are fair random draws from the model. They aren't cherry-picked, and they are completely uncorrelated. The adversarial framework successfully forced the network to actually understand what a number looks like and what a human face looks like, literally outputting reality from pure random noise. Now you might be wondering, how do we know the AI didn't just secretly memorize the training set? Which is a totally fair question. The researchers proved it didn't by using linear interpolation in the latent space, or Z-space, which is basically the AI's internal map of concepts. As the model moves from one set of coordinates to another, a 9 smoothly transforms into a 1. If it had just memorized the images, this transition would be this jagged, glitchy jump between two totally distinct pictures. Instead, this smooth morph proves the model intuitively grasps the visual, conceptual space between a 9 and a 1. So, distilling the massive legacy of this paper down to its core, before GANs, deep generative models required excruciatingly slow inference steps during training and completely relied on those clunky Markov chains we mentioned earlier. This adversarial model just shattered those roadblocks. Sampling? No difficulties. Inference during training? None needed. It traded a massive mathematical headache for a beautifully simple game of cat and mouse using standard backpropagation. It was just a staggering leap forward in computational elegance.
Which really leaves us with a rather profound final thought. Goodfellow's paper solved a major technical hurdle, absolutely, but it also opened a philosophical door that we are all still walking through today. When we successfully build an architecture where the counterfeiter perfectly replicates the data and the discriminator, the ultimate analytical machine, becomes completely blind, well, what happens to our definition of reality? If a machine can perfectly dream up a world that is indistinguishable from our own, the line between what is real and what is generated doesn't just blur. Mathematically, it disappears. Thank you so much for joining me on this explainer. I really hope this breakdown sparked your curiosity to look a little deeper into the amazing foundations of AI.